Welcome back to video 6.1.2. Moving right along in our 6.1 lesson, learning about thermodynamics. All right, let's jump right into another example. A student dissolves 10 grams of sodium hydroxide in 100 ml of distilled water and notices that the temperature of the mixture increases from 25 to 51.6 degrees Celsius. It's quite a jump. Part A, the student states that the process of dissolving sodium hydroxide is endothermic, because the temperature increases. So T, or delta T, the temperature is greater than 0. So that would be positive. So Q, then, is greater than 0. Do you agree or disagree? Use system surroundings heat, endothermic, and exothermic in your explanation. So I would like you to please pause the video, and if you don't write it down, at least think about how you would explain this by agreeing or disagreeing and using these terms, and then come back. All right, so welcome back. So I hope that you disagreed. If you didn't, it's okay. We're going to go over it right now. So disagree here. So why? First, we need to define our system. So the system is the process of dissolving your NaOH solid to NaOH aqueous. And the surroundings are the water that it all happens in. So let's write that down. The system the process of sodium hydroxide solid dissolving to sodium hydroxide aqueous, and the surroundings is the water in which it is dissolved. So we know that the temperature increased. So the student felt the temperature of that baggie increase. So we know that the water is increasing in temperature and that the heat must be flowing from the system that we just defined to the surrounding water. Okay, so since the heat is flowing out of the system, remember, the system is a sodium hydroxide phase change here. So since the heat is flowing from the system, out of the system, that means that this is exothermic. So it's exothermic with respect to the system. However, the water is absorbing the energy, so it would be endothermic with respect to the surroundings. But in general, if you're being asked about the process right here of dissolving this, you're being asked about the system. That's why we disagreed, because really this is exothermic. So this is exothermic with respect to the system. But endothermic with respect to the surrounding water. All right, part B. Explain in terms of molecular motion what's happening when the temperature of the water is increasing. Well, anytime that heat's transferred to the water, those water molecules are going to start moving faster and faster, and they're going to start vibrating, right? So that energy is going to increase molecular motion. We're going to increase kinetic energy of the water. So the temperature, which is a measure of the average kinetic energy of that sample of water, is going to increase because you're adding you're adding energy to it. So our heat is transferred to the water. So the energy of the water molecules increases. This energy increases the molecular motion, also known as kinetic energy, of the water. So the temperature, which is the average kinetic energy of the whole sample, increases. All right, so let's start looking at this on a more molecular level here. So describe in picture, so we're going to draw the substances before, so just the sodium hydroxide solid and the liquid water, and after the dissolution of sodium hydroxide, so forming the aqueous solution. Identify the inner particle forces involved in the substances before and after the dissolution. Do the substances before the dissolution have less or more potential energy than those after? Well, let's take a look at it. The first one I'm going to draw is sodium hydroxide, NaOH. Now that OH bond right there, that is covalent, but the sodium and the hydroxide polyatomic ion are ionically bonded. So since they're ionically bonded, we're going to have alternating positive and negative, making our sodium hydroxide crystal. So we have our positive sodium and our negative hydroxide here. So I'm just going to draw positive, negative, positive, negative. All right, so we have our small ones as positive. Our big circles are the negative hydroxide. And then right alongside it, we have water. So we have a ton of H2O molecules. These are in their liquid format. So we have H2O being, of course, oxygen and two hydrogens bound to it. So HOH. Now, the water is polar, and we've heard this over and over in all of our science classes. But water is polar, and we know that the hydrogen sides are partially positive, and the oxygen side is partially negative. So this little delta right here, that means partial. That's a partial symbol. And we know that negative attracts positive. So there are other water molecules in solution. So we have another water with a partial positive hydrogen ion side and a partial negative oxygen side. And then right here in the middle, we have some hydrogen bonding that's going on right there between the hydrogen and the oxygen. So this is before. Now what happens after? So these water molecules will actually go in and surround the different ions of the sodium hydroxide. So if you have, say, for example, the positive ion of the sodium hydroxide, so let's just draw one of the positive ions of the NaOH over there, it's going to be attracted to the negative ends of the water. So we will have our waters, HOH like this, attracted to the positive ions. And that's going to happen with many of the waters, right? So we have our H2O. They're all going to surround those ions. Now, conversely, we have negative ions, these hydroxide ions over here that need to get dissolved in our solution. And the positive end of the water is going to attract those. So if we have a big negative ion, we're going to have a whole bunch of slightly positive hydrogens wanting to surround that from the waters. And so we have all these waters arranging themselves around this negative ion, forming these ion dipole bonds. Intermolecular forces, really. So we're forming all of these attractions here. We're breaking some attractions and forming new ones. And so this will be our NaOH aqueous. So this is when it's dissolved. And you can imagine just drawing this forever in the same kind of pattern, just on and on and on. So let's describe what's happening in words before and after. So before. Before our ionic bonds, we have ionic bonds between the sodium ions and the hydroxide anions of the NaOH. So before there exist ionic bonds between Na plus and our hydroxide. There is also hydrogen bonding that is present between the water molecules. Now, after the dissolution happens, we're getting a bunch of different things going on here. Firstly, we have hydrogen bonding being formed between the H2Os. So we still have waters in our whole solution here. So if I were to draw another water, the hydrogen ion, so we still have hydrogen bonding happening between the water molecules there. So hydrogen bonding between H2O molecules. Let me grab another color and highlight this for you. So here's our hydrogen bonding right there between those molecules. We also have what we call ion dipole attractions between the sodium ions and the hydrogen and the water molecules. So we have ion dipole attractions between both Na plus and H2O and between hydroxide and H2O. And so those ion dipole attractions are between the dipole in the water here, right here, and the ions that are from the sodium hydroxide. So one of those would be there. Another one of those would be there, right? So we have all those attractions happening. Now we're going to look at this as it relates to energy. So describe the process of the breaking and the forming of these interparticle forces and the attractions and the bonds in the dissolution of sodium hydroxide. Draw a potential energy diagram over here for each step of the process. So this is going to be a multi-step reaction that we've looked at before. Then we're going to explain why the temperature lowers when dissolving a different salt, ammonium chloride. So why is that going to happen? So we're going to look at the series of bonds that are going to break, and then we're going to draw on our graph what's happening. So on the y-axis, we'll have PE for potential energy over there. So our first step that happens in this reaction is we're going to break these sodium and hydroxide bonds. So we're going to break Na plus 2 hydroxide bonds. Okay, and that breaking of those bonds, that's going to be, let's grab a different color, that's going to be endothermic. So breaking those bonds is going to require energy to go in to pull apart those bonds, right? And so step 2, we're going to break the water hydrogen bonding. So the hydrogen bond right here between the water, we're going to sever that bond too. And that's going to take energy to pull that apart as well. So we're going to break H2O, H2O, hydrogen bonds. And because that was also bond breaking, that's going to be endothermic because it requires energy to do. It's going to be endothermic. Okay, step 3. So we've broken all the bonds. Now we're going to start reforming bonds. We're going to form the sodium to water ion dipole attractions. We're going to form Na plus to H2O ion dipole attractions. And forming those bonds releases energy, so that's going to be exothermic. And then finally, step 4, we're going to form our hydroxide ion dipole attractions with water. So form hydroxide to H2O, ion dipole attractions. Okay, let's look at that in potential energy terms. So let's just say our reaction starting here on our potential energy. This is our reactants. This is where we're starting out. In step 1, we're going to break these sodium to hydroxide ionic bonds. That's going to take a lot of energy. So the potential energy overall of our system is going to increase to, say, this level. And you don't have to have this perfect on here. Like, the distances, not a big deal. We're just estimating. Okay, so that was from step 1. So this was step 1. So I'm going to label this step 1 so we know where things are. Okay, so step 2, break the H2O hydrogen bonds. Breaking bonds, of course, is going to require even more energy. So our potential energy is going to increase. That was step 2. Step 3 involved forming sodium and H2O ion dipole attractions. So forming a bond is exothermic. So we're going to release energy, and overall our energy is going to go down. And so this is from step 3. Last step, we're going to form hydroxide and H2O ion dipole attraction. So again, our potential energy is going to decrease. And we knew that this overall was endothermic. So it's important that I draw this final line for the products lower than the reactants were, right? Because this is what was this? So this is endothermic, so it's taking in energy. This one over here I forgot to label. This one should be exothermic. Okay, so the last part of this question says, explain why the temperature lowers when dissolving a different salt, ammonium chloride. Well, dissolving ammonium chloride is endothermic, and that's due to stronger ionic bonds or weaker ion dipole attractions, one of the two. If the ionic bonds are stronger or the ion dipole attractions are weaker, then you're going to have a different outcome. Then you're going to have an endothermic reaction. So let's write that over here. Dissolving ammonium chloride, as you can see, is endothermic. Due to stronger ionic bonds or weaker ion dipole attractions. Okay, and so then if we look at the original reaction that we had up at the top, so the original reaction that we had up here, we noticed that the temperature of the mixture increased there. So if the temperature of the mixture increased, that means that the energy that was released in this reaction was actually absorbed by the water, like we saw before, and that's why the student felt the bag get warm. Okay, part E. Calculate the heat flow for this process. And we're given the specific heat of water already. So we're going to calculate our heat flow, which is Q for our process. We're given our specific heat of water. This is just a Q equals MC delta T problem again. So the heat, and I'm going to write a little W here for water, equals MC delta T. So plugging everything in, again, this is from our original problem all the way to the top. So I'm pulling all my values from the very top of example 2. So that's where all these numbers are going to be coming from when I'm plugging all these in. Sorry, other notes. So we had 100 grams of water. We were given the specific heat of water, which is 4.184. I think we're just stopping at 4.18. And that's going to be in joules times inverse grams times inverse degrees Celsius. And then delta T is our change in temperature, so final minus initial. We end at 51.6 degrees Celsius, and we started at 25.0 degrees Celsius. Plugging all of that into our calculator, you're going to end up getting a positive value of 11,100 joules. So 11,100 joules. So that's how much water, or that's how much heat that the water absorbed. Now for part F. Calculate the delta H dissociation for this process. So delta H dissociation, what this is your bond dissociation enthalpy. And what that means is that's the enthalpy required to break 1 mole of a given bond, right? And so this is bond dissociation enthalpy. And we said that that was for 1 mole, so its units are in kilojoules per mole. Okay, so we know we're going to need to calculate this in kilojoules per mole. Now, the heat of my reaction is equal to the negative heat of the water. And that's because whatever heat the water absorbed must have come from the reaction, because energy can't just, it can't just like poof in and out of existence, right? So it's only going to be exchanged. It's not going to be created or destroyed. So the amount's going to be the same, but the sign's going to be flipped. So the heat of the reaction that we're looking at is going to be negative QW, which is negative 11,100 joules. All right, and we know this is per mole, and we're given grams, so we're going to do a quick conversion from grams to moles really fast. So the number of moles of NaOH. To calculate that, we started with 10 grams of NaOH, and its molar mass is 1 mole. And we have 40, I believe it's 40 grams per mole. And that gives us 0.250 moles. Plugging all of that in, delta H dissociation equals the heat of the reaction in kilojoules, so that's the top, over moles. So the number of moles, N for moles, in the reaction. And that number is negative 11,100 joules per 0.250 moles. So I want to be able to cancel out my correct units. And right now we're in moles of NaOH, but I want to do moles of reaction. Our balanced reaction is just 1-to-1 for this case, so I'm going to write it in just so we can see that. I might run out of space here. So 1 mole NaOH per reaction for 1 mole of the reaction. And I'm in joules, and I need to be in kilojoules, so we're going to do a conversion for that on here as well. So 1 kilojoule is equal to 1,000 joules. Sorry, that writing's getting a little tiny. And plugging all of this into your calculator, you end up getting negative 44.5 kilojoules per mole. There we go. So, negative 44.5 kilojoules per mole, that's what's required. That's the enthalpy that's required to break 1 mole of the bonds in this process of dissolution right here. Okay, that is it for video 6.1.2. I'll see you shortly for video 6.1.3.